Yes.
Okay, welcome everybody to the special colloquium today. Our today's speaker is Åke Nordland. It is my great pleasure to introduce Åke. Åke Nordland is Professor Emeritus at the Niels Bohr Institute, University of Copenhagen, where he works with colleagues and students on methods and application in computational astrophysics and plasma physics. During his PhD, he developed the MARCS stellar atmosphere code and subsequently pioneered the first realistic three-dimensional stellar atmosphere models, including detailed radiative transfer and realistic equations of state. This work evolved into the Stagger code and later contributed to the development of the Bifrost code for solar and stellar atmosphere modeling. His current work focuses on the dispatch code framework developed in collaboration with the ROCKS Center in Oslo and partners in Copenhagen, Cologne, Heidelberg, Göttingen, Barcelona, and Dartmouth. Dispatch is used to study multi-scale astrophysical plasma processes ranging from star and planet formation to detailed solar and stellar modeling. So today Åke will be speaking on the dispatch task-based code framework.
Thank you. This will be a hybrid presentation, a dual-purpose presentation, with the main purpose being to explain the new methods we're using. And to illustrate that, I'm also including some results, also for the purpose to indicate what would be possible in the near future by making good use of these methods. As you can see from this list of collaborations, the code framework is already used in a number of different contexts. In the first applications we did after writing the code was in star and planet formation. And we made really good use of it there and made things that are not possible with other codes. Some of these people are PIs or node leaders on a proposal that we just sent in a month ago. We'll see how it works. We expect results in May, perhaps. This is a new call from EuroHPC, which is the European Commission's organization for supporting high-performance computing in Europe. And they called for proposals to what they call lighthouse codes, codes that are shared among many different applications and that need support to become more user-friendly and so on. So the 4 nodes that participate are Oslo University in solar physics, Copenhagen and star formation, Cologne University, who are doing larger scale star formation, dwarf galaxies, and particularly are experts in non-equilibrium chemistry, which is also something we need in solar physics. And finally, Laurent Guisson in Göttingen, who is interested and an expert in helioseismology, which is also one of the really potentially rewarding applications of this code framework that does support self-gravity. It has a Poisson solver, so one can actually do G modes as well as P modes. So, concepts. What is a code framework relative to just a code? Well, it's something that invites adding things such as solvers and extra benefits. So it provides a number of services. Patch generators that generate your setup, list handlers that organizes the tasks, neighbor list handling, which organizes finding the neighbors of your particular data cube, interpolators, and most importantly, a task dispatcher that calls your solver of choice. And the solver is without any other responsibility than accepting a data cube, updating it. The data cube comes complete with guard zones. So it's like I call you instead of you call me, because the normal setup is the code calling a number of libraries, for example, MPI and whatnot. Here, MPI is in the framework, and it just calls the solver with one data cube, no parallelization, which comes instead from solving a number of these tasks simultaneously. As you can see, we already have a large number of different solvers, including the legacy Stagger and Bifra solver, but more useful, a number of Riemann solvers. And here I'm listing solvers in a broad sense. This is not how it works in the framework. There, a solver would be like an MHD solver, and a Poisson solver is a different thing that is added on top of that. So you can combine the Poisson solver or the non-ideal MHD solver with any other MHD setup. And likewise, for example, if you're interested in dust transport or something, that's an add-on, not a separate thing in a separate solver. So what is task-based computing? Well, it's like AMR, it's like adaptive mesh refinement, but in space-time, not just in space. So you split your entire problem into a large number of small tasks. And when I say small, I mean something like 16 cubed or 32 cubed or something in between. Often 20 or 24 cubed is a sweet spot. So you split the whole thing into a number of these small problems, and they can overlap. They don't have to overlap edge. They can overlap in an inclined way, and they can be different size. So in one application, we've done AMR over 24 refinement levels, which is like 16 million times in size. And I come back to the fact that it's a great benefit to be able to skew neighboring tasks so that you can cover, for example, a sphere with a number of perfectly cubical patches. So the dispatcher uses OpenMP inside an MPI rack. And nowadays, when you buy a node, it has maybe 256 cores, and it is split into maybe 4 NUMA regions, so 4 memory regions, and you can, for example, run 4 MPI ranks on each node, done with really good performance, and 64 threads on each rank, which launch updates of these tasks semi-independently. And these solvers need to know nothing about OpenMP or MPI. They just get a task, which is to compute one update. And one more task is to compute the fastest speed of propagation that they can tolerate. So these are then combined between different, for example, preconditioners into a time step. And that's the time step they are asked to update with the next time. As I mentioned, task guard zones are already preloaded, and tasks may overlap, even a lot. So if they overlap a lot, the one with the highest resolution will be the one that decides what the physical content is. And if you think about a task with the same resolution, well, is that a problem then? No, because they're separate in time. So they're never at the same time. And the one that's leading in time is the one that calls the shots. So we have a concept of NBOR, which is like a neighbor, but in logics. So an NBOR is a task that depends on another task, or that task depends on. And if you're thinking, for example, self-gravity, that might be not physical neighbor, but any task. And all of your tasks can thus be arranged in terms of dependencies. Radiator transfer is a really good example of that. If you have light going in one direction, then the task that is upstream is needed for the task that is downstream. And conversely, the task that downstream needs the one that is upstream. But they don't need the other ones. They only need the ones that have incoming light. So another really important concept is zoom simulations. It's something we have done enormously productively in star formation, where we take, for example, a region like 100 parsec cubed, and then we do star formation on intermediate resolution enough to form stars and let them explode and drive the whole thing. And we can then zoom into individual stars, for example, selecting the ones that become solar mass and study their accretion disks with up to a resolution of a small fraction of a parsec, so enough to resolve the disks around those things. Now, of course, when you zoom in on a disk like that, you're covering a very small time interval. So you're zooming in not only in space, but also in time. But the great advantage is you're doing it in a context where you don't need any particular assumptions about initial conditions or boundary conditions. You can leave the rest on. It doesn't have much to do, but it's there and it's evolving. So everything is consistent all the time. So what we're now proposing or doing already is doing the same in solar physics. So we're able to model the entire solar convection zone, including the surface with full radiator transfer, where the surface is not particularly expensive. It's like a few tenths of a percent of the cost of the thing, so it's cost balanced. So that gives the possibility to do exactly the same thing in the solar context. If you can develop dynamo action inside the convection zone, then you have the initial conditions that Bob were illustrating. If you just have flat, unstructured magnetic field, a few tenths of manganese below the surface, it develops spontaneously things that look very correct at the surface. So this idea goes further to take the entire convection zone and develop it on an intermediate resolution over a long time scale, and then zoom in space and time on active regions and doing the physics realistically there. So the current status and future perspectives include big simulations, because if we look at Matthias' fantastic corona simulations, that's the next step that's missing. To be able to use the sun as a physics laboratory where you can study particle acceleration and understand how it really works. So I think this is a really nice perspective for HAO with respect to NASA's HFR program. And it aligns perfectly with, I'm quoting directly from the call here, revealing first principle mechanism using system connectivity and emergent behavior. So the bottom line here is that chromosphere and corona dynamics should and can be seen, modeled, and understood in a global context if one uses this approach. So here's Matthias' fantastic simulations. And as he emphasized in a recent meeting, we need both large scales and high resolution and realistic physics. And my response then was that to do this is a tall order, but it's not impossible if one uses the zoom-in context. So one only evolves a small region with high resolution and high time resolution, and can then study that in a realistic context. In that context, one can use not only adaptive resolution, but also adaptive method. So I can put a PIC solver inside an MHD solver and have a criterion that says, I need it here, but I don't need it there. And since PIC is much more expensive per unit code time, per unit real time, it's not so much more expensive in terms of per update, but an update time is much shorter in PIC than in MHD. That can be balanced by the fact that particle acceleration and non-thermal behavior is only relevant in a very small fraction of the volume. So therefore, the cost balance can be okay. So first, a few things about the organization of the code framework. It uses object orientation. So everything is in small modules and can be better maintained that way. It allows, and I'll come back to that, spherical Cartesian volleyballs. So that's a way to cover a spherical region with perfectly quadratic or cubical data cubes. And in there, you can use adaptive mesh refinement, and you can have local method selection. Notice that the cost advantage here becomes larger and larger and larger the more complex the problem is. Suppose you simulate the whole galaxy, and then you zoom into a solar system and a planet and the moons around that. That couldn't care less about the whole rest, but it's part of the same setup. If one was forced to use a single time step for that entire thing, you couldn't do anything. The local time step is extremely crucial for being able to use the zoom concept. Technically, this is also the advantage that you gain cache efficiency. On a modern CPU, even 16 cubed is too much data to be efficiently using cache. So we have developed what we call paper solvers. This is a sort of joke on Axel Brandenburg's pencil solver. So the paper solver is one that uses a quadratic region. And that is the perfect balance. You can update sheets instead of data cubes. And then you get perfect scaling from 1 core to 64 on 128 cores on a rack. So that's why you get this near embarrassingly parallel OpenMP and MPI scaling. We have scaled it to 1 million cores. By the very construction, there's no need to send MPI globally and in sync. Whenever rank updates, it identifies those tasks that are needed by neighboring regions and sends copies of those tasks verbatim, the entire task, not just the overlapping part, to those other ranks. So we call those virtual tasks instead of the real tasks. And we call these that need to be sent boundary tasks. And that can be done without having to synchronize anything. The setup is solver agnostic. You can all of these extra features, non-ideal MHD, non-equilibrium chemistry, and so on. And the scaling is perfect. This is a plot showing two types of scaling. Weak scaling is when you take the same problem and you multiply it into many copies, and you increase the number of working nodes or cores in proportion. So each one has the same work. And then it's no surprise, perhaps, that the cost per update stays basically constant. The sloping line over here illustrates strong scaling. So you add more work to the same problem, and over like power of a factor of 16 or so, you get linear strong scaling as well. Interesting is this plot is 8 years old, and on it we see core at the cost of about 1 microsecond. That hasn't changed in the last 8 years or so. What has changed is you have more cores, basically. The speed per core is, okay, maybe a factor of 2 or so better, but not enormously much more than 8 years ago. So here's a direct illustration of the time step advantage. This is an example of a staggered code run that Bob and I did maybe 10 or 15 years ago. And it had 16 domains, 16 MPI domains with uniform time step. Now we take exactly the same slice in time, and we split it into 72 by 72 by 18 patches with 28 cubed cells in each. So then you have a really large number of tasks instead. Now we take a look at the cost of those as a function of the depth below the surface. And what happens when you have individual time steps is that the cost is the mean of the cost, not the maximum. If you have single time step, it has to be the shortest of them all, so it's the maximum cost. And you can see here that the difference between the mean and the max is huge. It's a factor of 30 in this case, and it would be even larger in the chromosphere and corona. So zoom simulations mean that you can use not only zooming in space, but you can also use adaptive methods. So you could use corona simulation, detect where is the current density large, and then you could add particle in cell there. And also one could, for example, decide that in the chromosphere, one would need non-ideal MHD or non-equilibrium chemistry. That's fine. Those can be added to any of the solvers. Now we come to another really important property of this setup, namely the ability to handle any geometry. I'll concentrate on the volleyball geometry in a few moments, but I'll just mention also that we have co-rotating cylindrical shells for accretion disks. That's something that works and is done. And the third one is an example that's clearly possible, but I haven't done it. You all, if you've read general relativity, have seen this example of an elevator. You drop an elevator in free fall, and inside it you have completely normal Cartesian geometry for a finite time until you drop into the black hole, and you're skewed into atoms. That can be done like this. You split the whole scenery into a number of elevators, and you follow them, and you let them overlap. And when you're tired of following it, you delete it and you start a new one, and let that fall. So it's clearly possible. And I hope somebody will do it sometime, but it's not done until now. So here's the volleyball geometry. If you look at a volleyball, it has 6 faces, and they're all identical. And each one of them is pretty much Cartesian. If in this case you think of longitude in this direction, so the long direction, and latitude is in the cross direction, then you can see that in the latitude it has parallel lines. So these are a constant latitude. And the face meets up with another face where the constant latitudes on that face instead is a changing longitude as a function of latitude on this face. So clearly you can fill this with cubical patches. And okay, we all know that the sun is 700 megameters in radius, And we would like to have something like 1 megameter patches. That's 1 part in 700. So that's a really small angle. It's an angle smaller than the angle extended by 1 cell over 20 cells. So the tilt that you have is less than 1 cell in each patch. And, this is actually to scale. So it looks like that if you fit them along constant latitude. If they were edge to edge, they would be in a great circle, right? And since they're not, they have to be tilted a little bit relative to each other. So what about the ugly corners then? Well, at the ugly corners, you have this overlap, and it's not a problem. I can show you a demonstration that it doesn't become a problem. And as for MPI, you can also use the fact that each face can be further split into 4 identical pieces, except for reflection symmetry. So you can have a quadrant, and therefore the lowest natural number for MPI is either 6 or 24 and upwards. So we've gone to 504. 1008 ranks is what we run on Lumi. So this is the way it looks in depth. You have this surface layer here with 100-kilometer resolution or something like that. And then when you go down to the next layer, the sound speed has already increased a lot. So in order to have about the same time step, the first step is typically a factor of 2 in size. And then the ones that follow have much smaller differences. So here it's not a factor of 2, but it's, like you have 20, and then you have 20, or you have 32, and then you have 28, and 24, and 20, and so on. So you gradually reduce the number of cores, and therefore increase the number of resolution cells. So the cost balance is that about 30% is in the surface layer, and the rest is evenly distributed over increasing sound speed and increasing cell size. So here's a concrete example. That is not anything else than a snapshot visualized with ParaView. So in this case, it doesn't have radiative transfer, but it has surface cooling and about 150 million cells covering the solar surface. And here is a flyby, which is closer to the sun than a Parker probe. And we zoom in and we can see the entire sun rotating. You can find this on YouTube by searching for Andrius Popovas flying over the sun. And if we go to another view, we see the entire sun like that. And there's no trace of the seams between the faces or the corners. They're invisible. So now let's go to a really important topic in solar physics, namely radiative energy transfer. We've done that since the 1980s, basically, by splitting the wavelength into a number of bins. And nowadays, it's popular to use about 12 bins. To have a reasonably good result, one needs at least 4 bins. And this has now been present in this batch since the very beginning, and is used by Maria Bergman et al. In Heidelberg to produce a number of models, network of models for the Foremost project. Very, very interesting results are expected from that. They had first light in October last year, and the outcome of that project is metal deficient stars down to -8. sounds fantastic. 100 million times less than the sun in about, that's what they claim to be able to detect. And for such stars, one has the benefit of low abundance means no uncertainties from physics. It's just hydrogen and helium, and a better separation of isochrones, which means a better age determination. Separately, a PhD student in her group has implemented multi-3D as a task implementation. Really, really nice. He's a fantastic guy, Richard Hoppen. They came visiting for a month in Copenhagen, and we were sitting together in the basement, and I started talking about the code and OpenMP, and I said, what is OpenMP? 3 days later, he had changed the Uppsala antique equation of state package to an OpenMP implementation. That's a capacity. What we do in stellar physics is diffuse radio transfer. We have parallel rays. What one needs to have in the interstellar medium is point sources. And the difference is not large. It just means that your rays are no longer parallel inside. And since we use short characteristics method, it doesn't make much difference, but we haven't done it until recently. So there's a postdoc in Dartmouth working on this. Significantly, it's done in a GPU-friendly way, because nowadays you can't get a lot of computing time unless you can do GPUs. But we found a really important improvement of traditional radiator transfer. It's actually not an improvement on top of what we did with the staggered code, because by accident, it is already conservative. The second order Fourier method is by definition conservative, and it's basically an accident. Conservative means that the energy absorbed in a cell is exactly the difference in flux in and out. So you conserve photons. You get exactly the right cooling at the surface. If you do it by analytical means, you'll end up with this quantity, the difference between intensity and source function. And when you integrate that over angle and frequency, you get the cooling, okay? So that's the radiator to equilibrium way of thinking of radiator transfer. You can instead do the divergence of the radiative flux, which is completely equivalent, and usually one say, that's just more complicated and less accurate because you have to take differences and so on. But in fact, if you use a solver that is, for example, third order in intensity as a function of optical depth, is not conservative unless you do this. And the only thing you have to do that is to ask for the answer, not at the center of a cell, but at the end of it, at the face of a cell. So it's just a small reorganization, but it increases the accuracy really much. As you can see here, this is from a paper you can find on Archive or on, I think, AppJ or ANA, where a particular line has been modeled. So this is post-processing and synthetic spectral lines with a number of depth zones, 60, 120, 240, and 300. Oops, sorry. And you can see that with the conservative RT solver, you can do away with 120 vertical cells, whereas in the classical RT solver, you need to go to like 450. And remember, this scales with a fourth order of the number of points, number of cells. So it's a really important factor. It can also be seen here in this plot that shows the result of a simple setup. You take Model S, Solar Model S, with no convection, nothing, just a 1D model. And you, in 3D, you compute the effective temperature of the radiation that it emits as a function of the resolution. And you can see that for the conservative method, the full drawn lines, it's consistent. The dependence on the time is consistent between the highest resolution and the lowest resolution. Of course, it's not exactly the same radiative effective temperature, but at least if you're asking not for precision, but for realism, you're fine. Whereas if you take the classical method, it simply deviates a lot and it goes the wrong way. So you can take surprisingly large time steps in optical depth. Like here, it's like almost an order of magnitude in optical depth between each point. So here are some examples with radial transfer solver and what it looks like at the surface in a cube with 33 megameters side and 47 kilometers cell size. And then the familiar thing that we all are now aware of is that when you go just a little bit 2.8 megameters below the surface, much less than the size of a typical cell, the topology has already changed dramatically. Now you no longer see cells, but you see the downdraft corners. And we go deeper down.
That's the source function.
Even more. Sorry, can we take it there?
Okay, yes. So,
so you have this sequence of merging to larger scales. And we used to think that this just goes on and on and on, but that's just because we didn't really think about what the convection zone looks like deeper down. We were so used to this thing that the density goes up dramatically with depth that we forgot about the fact that it doesn't. When you get down to like 40, 50 megameters, which is a small fraction of the 200 megameters, then the scale out stabilizes. So of the, I think, 9 orders of magnitude from the photosphere to the bottom of the convection zone, the last 2 fill 80% of the entire convection zone. So that means the need to go to larger scale disappears at some point, and you could in principle just plunge down with the same structure, which doesn't happen in almost, or in basically no models so far. I come back to that. So radial transfer is a little bit more expensive than no radial transfer. It could be a factor of 2 or so if you're eager to have many angles and many frequencies. But it's only necessary in a thin surface layer. So it's not a big deal when you think about the whole convection zone. Here's an example which is quite interesting in my view, where the cell size is only 10 kilometers. And we look a little bit below the surface and we find something that's similar, actually. It's an exponential distribution of the flux contribution, which is measured here. So this is the convective flux split into bins. So this is qualitatively different from laminar results, but it's qualitatively similar because it's still intermittent, with 50% of the flux is carried by only 3% of the surface area. So that's what happens when one goes to very high resolution. With adaptive mesh refinement, one can gain a lot because one can introduce high resolution patches where they're needed and only there. So here's an example where we look at adaptive mesh refinement at a depth of 24 megameters below the surface. And this is about the layer where the heliososmology measures large-scale flows. And we can see that with that image refinement, the results, those things, which are sometimes creating worlds and so on. If we look instead of entropy, this is entropy. If we look instead on vertical velocity in exactly the same place, forgetting about now the mesh, then it looks like that. Okay, so you see there is a really large intermittency between, but because notice that the color scale is symmetric, it's plus minus the same number. So we see that there is a big asymmetry between up and down flow. Not a big surprise since there is such a strong stratification that forces it to be there. And if we look at instead the horizontal velocity, for example, in x direction, we see another thing that's interesting, and of course follows naturally from intermittency. Namely, you have now blue and red mixed, very close together, because the x velocity changes sign near a downdraft. So that means that it complicates local heliososmology interpretations because scales are small. The signs of horizontal velocity, which is what they measure. They measure horizontal velocities, not vertical ones. They're alternating and features are moving. So of course, they're not taking power spectra at instances. They're averaging over time. So when you average over time, and features are moving, they cancel. Here's a volume rendering of the same thing from ParaView. It's a 54 megameter box, an AMR with 90 kilometer surface cells and 4 bin radiator transfer, 4 MPI ranks, 64 key cores each. So the color here is vertical velocity. You can see blue downward moving flow and in between weak upflows. The flow lines are streak lines, which is not really flow lines. In order to make flow lines with ParaView streamlines, you need time evolution so you can actually follow what one parcel would be doing. This is just a snapshot, but it still shows you how things are merging near the surface into coherent downdrafts and then end up in a more turbulent region when you get down to 40, 50 megameters. So in a very brief summary of an excellent thesis that you can find on archive, Bastian Proxaf's thesis from Göttingen, this illustrates how they do it. In order to measure horizontal flows in the inside of the sun, they take advantage of the fact that P modes are refracted and therefore they turn horizontal at some depth, and there they become sensitive to Doppler effects. Horizontal motions in either direction will shift and broaden the P modes, and from that one can deduce what the amplitudes are. One really great thing that Proxaf did was to sort out a number of misconceptions and a number of actual errors in papers. It's just so difficult to be consistent when you speak about power spectra and speak about modes, because you have to separate, is it the power per wave number or is it the power per log wave number? If you want to speak about the velocity amplitude at, say, a scale of 100 megameters, your eye is picking up a range of scales. So then it's the power per unit log that you really should worry about. And then if you go on to the fact that P modes are discrete, you can get even more confused. And what he did was to sort out all of that. And he found some significant corrections, but nothing serious. So the conclusion is still the same, that there is a fundamental discrepancy between models and observations, which is often called the collective conundrum. You can, with advantage, download his archive copy of his PhD thesis and read at least this section about the non-drum. So now over to something else. Particle and cell methods and results. So the first thing I'm going to talk about are old results from 2013. PhD student Gisela Berman, who used the photon plasma code, a code written basically by Truls Haugbødder, a modern high-order particle and cell code. And if somebody's familiar with particle and cell codes, they would know that charge conserving is one of the most important issues in particle and cell methods. If you just move particles and compute things naively, you will get a random electric field which causes artificial heating. So you have to move things in a conservative way. It's almost like the radiator transfer issue with conservative code. So this is a really great code which was used in a really great project in order to study a concrete example of reconnection in the sun. It's detailed in this paper from APJ 2013. And what we did was the following. We took a SOHO magnetogram and selected a region that had already been studied by other people. So we have a cutout like that. It has, as you can see, polarity of a different sign popping up inside here. And that's the cause of the null point that forms above it. So we start by constructing a potential field based on that. And then we let that evolve, driven by the boundary observations. So what that gives you is a null point theory with a dome and a spine, and that's consistent with observations that show traces of that dome and traces of the spine. I'll show it in a moment. So here we have a sliced current sheet, and we can measure, we can follow accelerated particles. This box is done with a PIC solver, and it's surrounded by MHD boundary conditions from an MHD solution. That box had 35 million cells and 3,000 billion particles, 3 to the 10 to the 12 particles inside. Most of those were wasted completely, because only in that region did things happen that were non-thermal. The rest was just a very expensive MHD. So the side view is like that, and there you can see the dome and spine. What happens when you do this stressing of the boundary is that you create DC electric fields that want to change that back into a potential, but it doesn't work because it's a near ideal situation. So that's the driver of everything that happens, and you get these current sheets. This is a vertical view and a horizontal view of the current density. And here you can see impact area of electrons in the edge of the dome, and that's exactly what you see also in observations. Here is the dome, and here is the end point of the spine over here. But the most interesting result from this, in my view, is the following. We looked at the power law of accelerated particles that we got in this case, which was close to the e to the minus 3/4. That slope means that most of the current was carried by high velocity, high energy particles, but most of the energy was in the no, the other way around, of course, because velocity is linear and energy is quadratic. So most of the energy was in the high energy, but most of the current was in the low energy part. So we now take a look at what do particle orbits or particle paths look like at low energy and at high energy. At high energy, you have a few particles, of course, because of the power law, but they go all the way from one end to the other. They succeed in catching the electric field acceleration all the way. We go to an intermediate energy that is less successful. Most of the paths are shorter, so they pick up less energy. But they pick it up through DC acceleration, not to any fancy Fermi acceleration or anything. It's simple DC acceleration. And here's the low energy side with even shorter paths. So you can think of it as you inject a number of particles, and only the lucky ones that find a good electric potential and find a good magnetic field to run along are successful. But because of the finite size of the current sheet and the random perturbations, most of them do not succeed to go all the way, which is sort of lucky, because otherwise you would short circuit the electric field in any case. So this, in my view, offers the most simple and straightforward explanation for the origin of the power law. It just requires a recursively decreasing fraction of space. So now over to recent publications from last year and related developments. This is by a PhD student in Copenhagen, Michael Hoare, who is now a postdoc at the Technical University working on more Earth-related plasma physics. So there's an opening there for somebody who wants to pick up from what he did. What he did was to develop dynamic method that couples MHD and PIC in a time-evolving situation. What we did in the previous one was study where the boundary conditions was basically stationary. So the first paper introduces a particle in cell solver, which is GPU-oriented, that is inside the dispatch framework. So it works as a task along with MHD neighbors. It's basically picking up after the photon plasma cone, and it's validated by solving standard problems that have no solutions. This guy, Michael Hoare, is really, really careful. He found things that we weren't aware of in the solvers. He actually found something which was clearly a bug in the MHD solver we have been using for decades, until we discovered that bug was cancelled by another bug. So it wasn't a bug. The bug consisted of using the French way of permuting XYZ. You go XY, XZ, which is wrong. You should do ZX. Well, anyway, it just shows how careful he is, this guy. So the method he introduced was to switch gradually from MHD to PIC. So half of the patch is used to fade in PIC. And once PIC is faded in, the other half is used to fade MHD out. That, he found, was the best way to get this smooth. So you can launch, for example, any type of LVN wave in the MHD part, and it propagates through the PIC part without reflection and stuff. Really good work. And here's the proof that it was actually correct. Namely, I mean, this is rather crazy. A two-state instability is a really complex thing, which shows wonderful complexity in the solutions, but it has a predictable growth rate. And that growth rate is a really good test of your setup. So you can see that it matches after growth to a significant energy, the thing saturates, of course, and becomes random. Here's another experiment that he did, the classical null-point reconnection thing. You can see it's evolving here in an MHD context, with plasmoids being created and so on and so forth. This is with constant resolution. And here's a zoom in with a PIC and MHD comparison. As you can see, the PIC does not evolve into plasmoids. You can say, oh, it's just because it's lower resolution, but I don't think that's actually the explanation. The physics is actually more diffuse in at the same resolution PIC. Finally, this technical thing, which is still really significant. When you buy an HPC system today, okay, you advertise that you have so and so many GPUs and they have fantastic performance, and 90% of your computing center delivers flops, which are GPU flops. That's at least the case in Lumi, Finland, which is the Northern European HPC center. But those nodes that have GPUs also have CPUs. And that should not be ignored. Instead, it should be utilized. So I found that the best way of using the GPUs and the CPUs in a hybrid fashion is we already had implemented bunching. So if you have GPUs, you have a really high capacity, which means you have to load it with a lot of tasks. And all those tasks have to be updatable. And in our dispatch setup, maybe only 5 to 10% of the tasks are updatable at any one time. So you need to have a large problem. But of course, that's what you have. If you have something which is suitable for GPUs, you have a big problem. So we order things into a bunch of updatable things, which shares or has memory on the GPU, which also allows us to use GPU with less memory than the entire problem has, luckily. But then instead of using only one bunch, if we have 3, we can prepare one bunch while the second one is updating and the third one is being post-processed and harvested for data that goes back into the first one. By doing that, we can keep the GPU 100% busy, no idle time, using only 10 cores to keep feeding it with new tasks. And this is the way it can be organized and should be organized in dispatch, because dispatch uses lists. And list things are not suitable for GPU, because GPU has to do things exactly the same on all of the. So this is how things are organized technically to obtain optimal GPU performance. We now have radial transfer, MHD, and PIC ported to GPUs. So to summarize and to make an outlook, we focus on realistic ab initio modeling, which means we want to have something that looks like the sun and works like the sun and walks like the sun, and probably, then it's matching the sun pretty well. And doing that, we can harvest enormous benefits by using task-based computing relative to the classical way that would make this not possible at all. And we take advantage of the strategy to use scale and method zooming. And those scale hierarchies provide initial conditions and boundary conditions that you would otherwise have to invent out of nothing. So that's the way to realize the Rosetta Stone idiom, namely to use the sun as a unique plasma physics laboratory. And in the dispatch task-based code framework, one can do full solar scale range modeling. So that's the final punch here. Thanks for your attention. And
Thank you.
question. Welcome, especially if you speak up, because my hearing is not the best.
questions?
I have a question. Oh,
Ragnar? And then
You said towards the beginning of the talk that for a full solar connection zone simulation, the surface layers only took about 10% of the computing time. Is that right?
Yeah, well, more like 30%. Yeah, okay.
Okay. I mean, the thing is, you have the shortest time scales and the highest resolution.
Yeah, it's just the way things work together. That the sound speed there is about 10 kilometers per second, and your cell size is 100 kilometers or less. And that gives you about a number of million cells has to be there to cover the surface. So that cost is nothing you can do much about.
No. Mhm.
And the rest is basically reverse engineering. You say, well, now I'm doing that. That's just about the same amount of work in the intermediate layer and in the deep layers. It would be a waste of time to spend all of the work at the top and have a crammy convection zone, and it would be a waste also to put all of the work into the convection zone and have a crammy surface layer. So it's not by accident; it's by construction.
And you
But luckily, luckily it works out because of the increase of scale height with depth.
yeah.
You're basically resolving the scale heights as well at the surface as in the interior. Nature is being friendly here. If one has a flexible setup, so one can utilize the friendliness.
So in depth, do you resolve time scales of sound speed? Do you resolve B modes?
Yeah. And the upshot is that the best one can do, which I've been doing the recent few weeks, is about 4 to 5 times the solar speed. So in 1 week of computing, you can do 4 to 5 weeks of solar time. It's completely independent of how much of the sun you're modeling. In this case, I'm modeling like 25 megameters on one node, or half a node. 128 cores can give me that speed on that size. I could expand it to the entire sun simply by having as many cores as needed. Probably something like 100,000 cores. Then I could do exactly the same all over the sun at the same speed. I can't beat that speed because I need the number of tasks.
Mm-hmm.
And if I reduce the resolution too much, I don't have enough tasks. So it's a sweet spot, but it's okay. I mean, it would be worse if you had 4 to 5 times the solar. 11 years in 2 years is pretty okay.
Alina.
I have questions, if I may. The first question is about visualization. You showed some flow lines, if you want to go back to.
Yeah, with ParaView.
And with ParaView and those tracks. Did you specifically show some specific lines, or is it whatever it's coming up
Okay,
with the
yeah.
simulation?
The way it works in ParaView is that you launch these from a line, okay? So it was just a single line across the surface. So it's randomly picking up whatever that intersects.
So you chose the lines.
Yeah. It also has a volume source you can choose, but that's a spherical one. So, actually, much better than showing that is to actually show the. I'm not sharing this. Okay. Let's see. I can probably. I missed this before, but I have it actually online here. So the point I wanted to make is that once you have it interactively, you can move this line. And that really is great in trying to understand the topology of things.
So you choose different field lines everywhere where
Yeah, you
start.
can move the where you start,
Yeah.
and sort of probe around and look for things.
Okay, so what you showed us is your choice of visualization
Yeah.
of those specific flows. Okay, so if you have another question, I don't know if you want to go back to the slide where you have those tiles of simulations, small piles of convection squares or whatever. They looked, maybe that was just another tool for visualization and show it to us.
Yeah.
And further where you have the full disk. And
Was that showing
the alignment of those tiles.
it was demonstrating the volleyball,
Yeah,
planar approximation for the volleyball.
go backwards.
Not sure where we are aiming for.
back.
Way early.
What's the question?
So the question is, those tiles to me looked, maybe it's just because you did copy paste, they looked identical,
They were.
close enough. Maybe the previous one, one more, one. Yeah, okay, you zoomed in. The next slide, and then you zoom in a bit. Yeah.
Oh, yeah.
Yes.
Okay,
Okay.
here.
So these are, I don't know if this is a true simulation or, because to me they look identical.
They are. This is only for illustration.
Okay.
Yeah,
But
they
in
are
real
identical.
simulation.
And there aren't any boundaries in between
That's
either.
what I thought. But
just-
in real simulation, if you,
Yeah.
because I still don't understand how you do the coding, there are lots of technical things. Let's
But
say the boundary condition of one tile,
yeah,
if maybe I don't pose the question right, but if you have boundary condition for one tile, how are they at the connection between the next tile?
yeah,
How do they respond to each other?
yeah, right. I already mentioned that the only displacement is less than a cell. Okay, so that is not really the most important thing. The most important thing is that when they have a tilt and you have an x velocity here, that has to be exported to this guy as mainly an x velocity, but also a vertical velocity. So that's where the spherical geometry comes in.
Mhm.
Of course, when you do things on a Cartesian thing, you're not really catching the sphericity, except the direction of gravity is always correct. So the surface of one individual patch is a little bit round. It's not flat.
Okay.
But the vector connection between one and the other in magnetic field and velocity has to be done correctly. And that's technically a bit messy, especially with magnetic fields which are staggered, half cell phase centered, but that's a technicality.
So you do this matching by the numerical.
And now
vectors.
think of this edge, okay? It looks fine here, but the other patch, which is bounding here, the other face, comes in with patches like that.
So, yeah.
So that's a case where you have overlap that's substantial.
And if there is a disturbance that may happen somewhere, we think had some physics connected.
Yeah.
How would that disturbance
Propagate.
propagating and be absorbed in the neighborhood?
Propagates when you load the guide zones from where it's coming from. If it's propagating to the left, it's coming into the guard zones of the next task. So the way this time step freedom is implemented is that every task saves 5 or 6 older time slices, so that when another neighbor needs filling of guard zones, it can get the right time. A certain extrapolation is allowed, like 10-20% of ahead of time, but that's exactly what partial differential equations do. They extrapolate in time. They guess the next state. So that's how it works. And that's independent of how much you happen to twist things. And as I mentioned, there's never a conflict because there's always one that's ahead of the other one. Huh?
Okay.
Thank you.
Okay.
Here's a question.
So you claim the entire convection.
Yeah. The entire convection zone, yes.
And
4 times.
I find you that you can not do a whole solar cycle. My question is, if you do the entire convection zone, you reproduce differential rotation.
That was my question.
We haven't tried that yet, huh? But I should correct you in
But
that.
that's the most important question.
Yes, yeah. But you're correct. If we do the exact entire convection zone, including the surface, then we can only do 45 times. But if we stop 1% and not at 40, 1/10%, 0.999 of the solar radius, and replace the surface with an artificial cooling, then we can move much faster. And this is classical. I mean, the first time I came here, I came as a guest to Peter Gilman, and he was doing 3-dimensional models already then.
Sure.
But they were only going to 90% of the radius. So that's a compromise you have to make if you want to do full solar cycles. But it brings up another point, namely, how do you understand solar differential rotation from modeling? Well, you have to learn by your own mistakes. But there are 2 ways of learning from mistakes. You can start from, arbitrary initial conditions and fail to get the right answer. And then you have the right answer as observations and your own model, which is not matching at all. And you're probably in a tough spot to explain why there's a difference. But if you start with the correct differential rotation imposed initially, and you run and you find that it starts to deviate, then you can investigate why does it deviate? Why is it not in balance? That's a much better approach to understanding how it should work.
Well, that's whether you don't know yet, but it's a different approach. And I think I glad you should do it.
Yeah, I'm not sure. I mean, I don't think this has a final solution, although one has learned a lot during the last few years. But now I understand that there's a progression in Rossby number from one domain to another, and the sun is not far from a boundary between the two. So a lot of progress has been made, but I don't think one can claim that one perfectly understands differential rotation yet.
Oh, this is why I say that's sort of the most important problem to attack. If you can do this.
Yeah, it's a key problem. And an expensive one.
When you were showing the zoom in approach, look at the finer scales, is there information or that propagates back from those smaller scales into your larger scales effects?
Yes, absolutely. And the way it travels back to larger scales was really good, illustrated by the visualization, namely that the this looks pretty much like a tree structure, where the small scales become larger and larger and larger because of the overturning convection. So the larger scales are carrying the smaller scales. It's an advective feedback. And it's always an issue in dynamo theory, for example. How much is transported to smaller scales? How much is transported to larger scales? So that's part of a central part of the problem and the solution. Get that coupling correct. And as far as I understand, nobody has done it correctly yet. Maybe the people in Göttingen are close to publishing the breakthrough paper. You have any news from that?
Interesting, yeah.
He wouldn't tell us if he had.
Yes, you have a question.
Yeah, I had a question about simulations of the corona with peak treatment and balance. I mean, the scale separation between the peak scales, which are naturally at the meter or so,
Yeah.
and where you do MHD, it's something like 6 orders in magnitude. So likely you do some AMR to get the MHD scales to something smaller, but I think you likely also want to do some artificial increase of the peak scales to meet somewhere in between. Where do you think is kind of the sweet spot?
Yeah.
Meet there in the middle.
This is a common knowledge in particle and cell simulation. You can not do them honestly in most cases. Actually, the solar case is one of the most close one to being done honestly. In many cases, one messes with the speed of light in order to increase the time step. That's not so much necessity in the solar context because the Alvean speed can be 10% of the speed of light, so it's only a factor of 10. The main issue with PIC and the sun is indeed the difference of Debye length scale, which is impossible to resolve. But remember, what does the Debye length really mean physically? It's the scale above which charge neutrality holds. So I don't think it's extremely important to be able to resolve that scale down to meter size or centimeter size. It can always be tested, of course, with, and part of what Michael Hoare did here was to actually test what that assumption, messing with assumption does. He introduced something called physical adaptivity or something, where one messes with the physical constants and investigated what that means in terms of results. But it's done all over the place in history, in tokamak research also, that one faces this challenge of disparity of timescales.
Did you say that it's about that the work of the framework in calculating what has to go from one cell to the next is about 10% of the total work? What I'm interested in is some of the time is spent in the server and the other time is spent in the framework and getting all the data right.
Yeah, that's roughly right. About 10 to 15% is spent in communicating guard zones. Another 5% is spent in the equation of state, lookup table, and at the end, between 55 and 60% is in the solver. Most of the time. If you do adaptive mesh refinement, it's probably a smaller fraction because you have, in that case, many more guards, many more neighbors, up to 60 or 90 neighbors of each task. So.
Does that depend on how distorted the different patches are?
The cost increases or the cost imbalance gets worse if you have very large differences between time steps. So if you have, for example, a few patches with very short time steps, well, they tend to take up most of the cost. And there is a module in this code called the Mulligan model. If anybody plays golf, then you know what a mulligan is. That's when you play the ball again. So if you have, for example, a supernova, and it goes off a very, very cold medium, the cold medium takes a long time step, and the supernova comes along between two time steps. So that defeats causality. And then you have to detect that and play the ball again.
Question, Ragnar?
With the whole solar connection from simulations, how do you deal, do you get a thermodynamic equilibrium with the convection and the deep part? I mean, the thermal time scale.
We haven't succeeded with that yet, but I think it's shorter time scale than one might imagine. If one just takes naively the Kelvin-Helmholtz time scale, then you can just fold and do something else.
Mhm.
But if you also combine it with the fact that you're asking for relatively small changes, very small changes, then I think it's a pretty good hope to be able to start out with Model S,
Mhm.
which is a very well-defined empirical structure of the sun. Then you should be able to, in a few turnover times, get things basically right. I'm sure there will be an initial spike.
Yeah.
And I suspect very much that the initial spike is what is killing the many attempts to get the low amplitudes. Because if you have an initial spike that drives large scales, then good resolution is working the wrong way. With good resolution, a large mode lives for a very long time.
Yeah. Yeah.
So those bad results could all be caused by initial conditions. I don't know how many turnover times people have afforded in the past, but I'm sure it's always a balance between trying to have high resolution and a long time evolution.
Yeah, how close you get to the surface.
Yeah.
When you do the radiative transfer, is that done as a separate task?
We've done both. Right now, it's not a separate task, but it should be probably. Especially when you're doing point source radiation, it must be separate tasks. And it's a good thing to have separate, because you get more tasks. And the more tasks you have, the better you can parallelize.
Yes.
Yeah, I had just one more comment regarding Reiner's comment. I think the big challenge arises if you go deep enough that you also include the overshoot region.
Yeah.
Because the time scales involved in relaxing that can be way longer. And the problem is, right now, I don't think we have any model which describes that well. And I think there's a lot of discrepancy between helioseismic constraints and the structure of overshooting, but any model kind of shows. So it will be hard to start off with something good there.
Who would you say are currently in the top working on that?
I'm not sure really if anybody is actively working on it. I only know the one thing is, I mean, there are some helioseismic constraints on the smoothness of these transition regions from nearly adiabatic to the radiative gradient.
Yeah.
Because if it would be too sharp, like classic non-local mixing links,
And remember,
then there would be some seismic signals which
that's exactly where helioseismology is beating us on the head and saying you're wrong.
Yeah.
That's where it doesn't match.
Yeah.
And things resolved that transition helioseismically.
Yeah.
Which is,
I mean, the problem is it's much smoother than most people think it should be based on typical estimates, right? Because if you have a very smooth transition in the overshoot, it will require that some convective motion have to penetrate into a strongly subadiabatic region.
Yeah.
And that requires a lot of kinetic energy. You need the spectrum with some very fast downflows in there to make that work. And that has not been completely resolved.
I don't remember, were you at the Nordita workshop?
No, I was not there.
But there was a lot of talk about what's it called, that region, Dierdorf region, where which is not the overshoot region, but the region where the radiative energy is decreasing to zero. there's that region is quite extensive.
Yeah, it is quite extensive.
There's a lot of heating going on there. And therefore, when your cold stuff comes down, it's being increasingly increasing the contrast. But the
Yeah.
background is
Yeah.
getting hotter because of the heating of the upflow.
You're talking about the bottom or the top?
Yeah.
The bottom of
Bottom.
the section, so, or the bulk actually.
Yeah.
Actually.
Right. Yes.
So does that mean that Russian radiative transfer is included, diffusion radiative transfer is included in the bulk?
Well, we talked about that. It's so cheap to do radio transfer with one bin
Mm-hmm.
that it would be more consistent to do it with the Rosland mean defined by the bins.
Yeah, okay.
Then you would be ensured that they would be consistent. But right now we have a separate radiative diffusion module,
Okay, okay.
the classical.
We have the same issue at the bottom of the convection zone in that there's the opacity is changing rather slowly. And so there's a large region in which you get radiative heating from the interior
Yeah,
into the convection zone.
yeah, yeah. Yeah, it's a complex thing. But I'm not on top of the work that has been done so far.
I don't think anything has.
How would the radiative core have to be handled differently if it contained
All right.
a greenhouse primordial field of something like about a house?
Picture says, even though I closed my.
Still connected.
Okay, let's thank our speaker again and then